Hello everybody. So in this video we're going to prove the product formula over Q. So this says that if x is a non-zero rational number, then if we consider every possible absolute value on Q, which we know by Ostrovsky's theorem that these are the p-adic absolute values where p is a prime number and the usual absolute value, then if we consider this a priori infinite product, this is in fact equal to 1. Now, before I move on to the proof, let me just make some small remarks. Well, first of all, as I already mentioned, when I write the absolute value of x at infinity, this is just the usual absolute value. And this is, by definition, this is the p-adic absolute value. Okay, so before we start proving the theorem, I would like to briefly recall how can one define the p-adic absolute value. Okay, so let me make the following remark or reminder. So okay, let's say in order to build the p-adic absolute value, to define it on Q, first of all we start with integers. So let n be an arbitrary integer, and we define Vp of n, which I think it's most of the time this is referred to as the p-adic valuation of n. This is the largest power of p that divides n. Hence, we can always write, if n is an arbitrary integer, we can always write p to the power of Vp of n times m, and p can divide m. Now the important observation, well, which is actually really simple, which I'm going to use later, is that that if n is an integer, then this is actually 0 for all but finitely many primes p. Right? Simply because every positive integer only has finitely many primes, prime divisors, right? Okay, so once we have defined this Vp on Z, we can actually extend it to Q with the obvious way. So Vp of x, where x is some rational number written as alpha over b, then this by definition this is just Vp of alpha minus Vp of b, right, for every rational number. Now the p-adic, one can show that this is a well-defined operation. Now the p-adic absolute value is a function going from Q to the positive to the non-negative real numbers, taking a ratio alpha over b, and it maps it to 1 over p to the power of Vp of x. So the important property so the important property of the p-adic absolute value it's that it's non-Archimedean. So by definition, what this means is that if I consider the periodic absolute value of the sum of two rational numbers x and y, well, since this is an absolute value, by definition we know that it satisfies the triangle inequality. But when I say that the absolute value is non-Archimedean, what we mean is that this is less than or equal to the maximum of the absolute values, which is a rather strange property. Anyway, so now that we recalled how can one define the periodic absolute value in Q for every prime P, let's try to prove the theorem, which is actually not that hard to prove. Okay, so the first observation is the following. In order to show that that this equality is true, right? In order to show that this red star is true, it's enough to show the same thing, but not for rational numbers, but just for integers, for positive integers, right? And this easily follows from the fact that every absolute value is multiplicative, right? So let n be a positive integer, and let's write n as let's write the prime factorization of n, right? Okay, now it's really easy to calculate this product, simply because all but finitely many of those absolute values are actually going to be 1, and therefore they're not going to affect my product, right? Okay, so we have, okay, so if I take this product, okay, so if P is a prime that it's not equal to any of the Qi, then Vp of n is going to be 0, right? Because P is not going to divide 0. And therefore the absolute value of n with respect to that prime number P is going to be 1, right? And therefore these number ones in this product, they're not going to affect my product. Therefore we can actually write that this is equal to this guy over here, right? So this is just right. This is just this, and now all we have to do is just apply the definition. So this is just right 1 over q k 3q k of n, and this is, and as we said, the absolute value at infinity is just the usual absolute value, and since n is a positive integer, we just have q1 r1 q kappa qk rk. Right, but now since this is exactly equal to 1, since vqj of n is just rj for every j that lies in here, right? And this actually finishes the proof. And before we end this video, I just want to mention that there are several generalizations of this theorem, and in fact one can prove a product formula for every finite extension of Q, right? For example, it's easier to do let's say for Qi, but yeah, but one can also prove something that's actually even more general than this. So thank you for watching.